Um, I would like to continue talking today about the limitations of Turing machines. So if you recall, I'm going to draw that little sort of diagram of languages here. We have the regular languages. That's the simplest ones, including such greats as a to the n. And then a larger category would be the context-free languages, which includes a to the n, b to the n. That's a context-free, but it's not regular. And then we have two larger categories. The first is recursive. That would be languages that you can accept on a Turing machine which never has the possibility of an infinite loop. So this category here, if you recall, this is Turing machines with no infinite loops. And a good example of a recursive language, which is not in the other categories, not context-free, would be a to the n, b to the n, c to the n. Right? We've done that example using a Turing machine that marks off the letters. And that Turing machine that we use to do that language, if you look carefully at it, you will realize that it is not possible for that machine to enter an infinite loop, just because of the way we made that. You mark off a A, then you go to the right, mark off a B, go to the right, mark off a C. There's no way that process can have an infinite loop. So that is an example of a recursive, but not context-free. The largest category here is what we call RE, recursively enumerable. This would be Turing machines, but sometimes they allow infinite loops. All right. And today I want to talk about a language which is in this category, but not recursive. That is to say, you can do it with a Turing machine, but such a Turing machine must sometimes cause infinite loops. All right. So the big question for today is sort of what's in here. All right. This language that we're going to talk about. So that means that this language can be accepted by a Turing machine, but sometimes that Turing machine allows an infinite loop. I kind of already wrote that. This language that we're going to talk about today can be accepted by a Turing machine, but sometimes it loops infinitely. What that means is that that machine as a practical computing instrument is not actually all that great, because it means that sometimes you will be, in practice, you'll be unable to tell the difference between when this machine has entered an infinite loop versus when it's just like trying really hard to solve the problem. So this language can be accepted by a Turing machine, but can I say, like, not a good one, not a God one, not a good one. That is to say, it might be looping, but you can't tell. This is like a real world computer. It's like this. It might be entering an infinite loop, but there's no way to tell from the outside whether that's happening or whether you just need to sort of wait a little bit longer. All right. So let's try and talk about this. All of this this language here does not have a nice formula in this sort of tradition. You might think, well, what about a to the n, b to the n, c to the n, d to the n? Actually, that is also recursive. You can make it easily adapt this marking machine to do the same language, but with a d to the n. So adding more things there does not get you any different categories of languages. Out here, this language is going to be truly weird. Like, this is the kind of thing that you would not think up on your own, and it cannot be expressed in any kind of ordinary formula like this. But anyway, the language that we're going to talk about today, this has to do with, it's about simulating other Turing machines on a Turing machine. This is something that I sort of mentioned last time, something that probably we all are familiar with, the idea that a computer can simulate another type of computer, or it can even simulate sort of its own type of computer. Like if you've ever developed apps, phone apps, you probably do that on an ordinary computer, like a laptop or a desktop computer, and then you run some kind of Android simulation or even an iOS simulation. I've actually never done this, but this is how they do it. Or if you're developing games that run on a game console, you do that on an ordinary computer, and then you use that computer to simulate the console that you're developing for, whatever. So you can simulate any kind of computer on any other kind of computer. Now, it's difficult, although theoretically possible, to say simulate a modern Windows computer using an Atari console. Like, they are both computers, so in theory you can simulate one with the other. It's just you would never want to do that because the one is far less powerful in terms of speed. But as abstract theoretical instruments, they're all the same, and any one of them can simulate any other. That's all I'm saying. Sometimes people ask me, like, does this mean you could play Doom on a Turing machine with the tape and all that? And my answer is basically yes, although you as the player would have to figure out how to read the tape as a coherent, screen on Doom or something like that. I wouldn't recommend it, but from an abstract point of view, yes, you can simulate any of these machines with any others. Okay, so we are talking about simulating other Turing machines as on a Turing machine. Now, what would it take to actually use one Turing machine to simulate the activity of another? What you would have to do is, if you really wanted to work this out, this requires somehow taking one Turing machine, let's say M, and then if you want to simulate this on another Turing machine, you have to sort of encode M in a proper format that can be used as the input to another Turing machine. So this requires taking one Turing machine, which I'll call M, and then encoding it somehow as a string. This would involve translating the diagram of states into somehow a big string. Now, we usually draw the diagram of states as a diagram with like shapes and arrows or whatever. But it is possible to encode such a diagram as a string. I hope that you believe that's possible. You would just somehow have to write out the structure of the diagram in a string form. This is possible. So you would take one Turing machine, which is M, encode it as a string, and then also encode the input to M. Let's say, some little string X. Remember, we're imagining taking one machine and its input and simulating all of that in another Turing machine. So you would encode M as a string. You would also encode the input string. I mean, that's already a string, so you don't have to do much work to that. And then our sort of, the machine which is doing the simulation, I will call a universal machine. Takes the input like its own input is something that looks like M hashtag X, where that hashtag is just a separator so that you can tell the difference, where this is a string encoding of M, and then this is some input string. All right, so we have some kind of universal machine which is running the simulation, and its input looks like that. It looks like a machine that is a string encoding of a Turing machine, followed by some input string on that machine. And then what the universal machine does is it runs a simulation of the other Turing machine. All right, this is all fairly complicated if you really want to do this in practice, but actually people have written down the details of this, and it's not so bad. And in our book, actually, they describe exactly how you could encode a state diagram for a Turing machine as a giant binary string of zeros and ones, which I didn't think it was worth going through the details. I hope that you believe me that this is all possible to do. All right. After all, everything that runs in your computer is on some level encoded as a binary string, and so I hope that you agree with me that basically any kind of information that you would ever want, you could, in theory, encode it as strings. All right. Anyway, our universal machine is going to take input that looks like that, M followed by X, and then we can simulate it. That is to say, what I mean by that is the language what I mean is that U takes this as its input, U being the universal machine, M hashtag X, and then it is accepted on U if M accepts X, and it is rejected, if M rejects X. U is a simulation machine, and it just does the same thing that the original Turing machine does on that input. And it also, loops forever if M loops forever on X. All right? This machine is running a simulation of the original Turing machine. This is possible to do with Turing machines. That's what I'm trying to say. All right, and this whole thing about simulating one machine with another one is the basis for our weird language, which is recursively enumerable but not recursive. This is our non-recursive language, and it is. This is actually a famous thing, which I don't know, you might have heard of. Our non-recursive language is based on a famous problem called the halting problem. The halting problem. The halting problem is a sort of question that you could ask about a Turing machine, and it says, given a Turing machine M and some input X, can you determine if M halts with input X? That's what the halting problem is. If I show you a Turing machine and I also show you another string, can you tell if M is going to halt or not on that particular string? Now, if I really did this, like as a homework problem, say, I show you a Turing machine and I show you a string and I ask you, does the Turing machine halt on this string? How you would answer that is, you would just try to do the Turing machine with that input and see if it halts, that is to say, if it's either accepted or rejected, versus entering an infinite loop, all right? So this is something that if I gave you a specific example by hand to try out, you could probably figure it out. Although if the example was really super complicated, it might take you a while and it might be difficult if it was a huge diagram or something like that. All right. What I want to do is I would like to consider this kind of problem, but encoded this as a language. So a sort of language version of this would be something like, I'm going to call it L sub H. This is LH, meaning the language of the halting problem. And the language is defined like this. It is all strings of the format M hashtag X, such that M is a Turing machine. What I mean by that is some string encoding of a Turing machine, which halts on X. M is a Turing machine which halts on X. All right, that's the language. Actually, you can fill that into your little diagram. That's the one that goes right here. LH. The language of the halting problem is recursively enumerable but not recursive. What that means is there are Turing machines that can compute this, but those machines must sometimes enter infinite loops. That's what we're going to try to demonstrate here. And then I want to talk about sort of what that really means. This, I don't know if you feel this way, but this might seem hopelessly abstract. Actually, this is very much important and encapsulates some things that probably you already know on an intuitive level about computing machines. Anyway, the question is, is LH recursive? And is it recursively enumerable, right? The answers are no and yes, but that's what we're going to demonstrate to show that LH actually is in that category of languages that I said before. Let's talk about RE first of all. It is recursively enumerable. Can we try to explain why? I put it there in that category in the diagram. It is recursively enumerable. This means it is possible to make a Turing machine that can decide if the machine halts on X. It's just that sometimes that Turing machine will run forever. And so how do we do that? This is actually, all you got to do is run a simulation. So LH is recursively enumerable. This is because we can make a Turing machine which simulates M, right? So if M halts on X, our Turing machine simulation can be made to accept X. You just run the simulation, and if the simulation stops, you accept. And if not, well, if not, it runs forever. That's the issue. But if you're talking about just being accepted or not, you can make a simulation of the original Turing machine, and if that Turing machine halts, then you accept the string. All right. So this one will accept. So our simulation accepts any M hashtag X if M halts on X. All right. So the it accepts LH. All right, and that means LH is accepted by this Turing machine. The problem is for strings which do not halt, this Turing machine will run forever, and you're never going to get a sort of a satisfactory conclusion whether a certain string is rejected or not. It'll run forever. But if you're okay with that, then that means there is a Turing machine which accepts this language. It's just that sometimes for strings which are not halting, it's going to run forever, and you're actually, from a practical point of view, you're never going to realize. All right. So anyway, that demonstrates that LH is in this category. All right. Now we have to demonstrate that it's not in this category, and this is the more interesting part. So for the next few minutes, I want to try to explain why LH is not recursive. All right. So this is kind of the two steps here. We already showed that it is in the RE category, but it is not in the recursive category. This is kind of the hard part, and this is, although it's not really hard when it's presented to you, it's a little confusing and it's very strange. Probably you have not seen a mathematical proof of this type, and actually, I don't know of proofs in other areas of mathematics that follow this kind of structure. This, to me, when I see this kind of proof, I have only seen used in this kind of weird Turing-style algorithmic mathematics. But anyway, the proof idea is very similar to a strange sort of logical conundrum that I remember hearing about when I was a kid about somebody who says, I always lie. Have you ever heard of this? This is like a weird logical paradox. If I say I always lie, am I telling the truth or not? Well, if I'm being truthful when I say I always lie, then actually that means that I always lie, which means that I must not have been truthful. So I'm not being truthful if I say I always lie. But am I lying? Well, if I'm lying when I say I always lie, then that actually means that I do not always lie, which means that I sometimes tell the truth. And this is also contradictory. So there's some kind of paradoxical nature to a statement like that. And so this is a strange thing. All right, that's what this proof is like. It's sort of a proof by contradiction, which constructs an immediately like self-paradoxical scenario. And it involves weird things. Like, what's weird about me saying I always lie is that I'm making a statement about myself, and the statement that I'm making also says something about the statement that I'm making. Like it's a self-referential kind of a thing. And that causes weird logical situations to arise. And that's what is going to go on with this. So this is based on, can I just say, this is going to be a proof by contradiction. So I will say, to get a contradiction, let's assume that LH is recursive. That means we have a Turing machine, and I will call it, I'll call it N. Which accepts LH, that is to say, it's all strings like this. And never loops. Right? That's what it would mean that LH is recursive. It means there's a Turing machine which can accept this language and never loops. That means it can always just straight up tell you, does it halt or does it not halt? Because in the other one, which sometimes loops, it can tell you if it does halt, but sometimes it will just loop forever and you'll never know. This one actually can tell you, so I'll say N can always give like a yes or no answer of whether or not M halts on X, all right? And the weird sort of self-contradictory situation will arise when we try to do this. We're not going to get here for a few minutes, but where we're going with this, just to give you a little spoiler, we're going to ask about what happens when we run N on N hashtag N. This is the weird situation which is going to lead to some ridiculous contradictory scenario. That is to say, if I take this Turing machine and run it on itself with itself as its own input, you're asking the machine to simulate itself, or really it's not simulating, it's asking if the machine will halt, if its own self will halt, when its input is also its own self. This will lead to some very weird situation, which is where we get the contradiction from. That's where we're going with this. All right, let's see if we can work this out. So N tells you if the machine, what did I say? N can always give a yes or no answer whether any Turing machine halts on any input. All right, this is the idea. What's contradictory about that? What this means is we can create some Turing machine which I want it to work slightly differently. I want it to work the opposite way around. This is kind of like the I always lie Turing machine. So this is a Turing machine which I'll call, I don't know, K, so that if the input is actually M hashtag M, then I want to make a new machine so that K halts if M doesn't halt. It just does the opposite. So this is a machine which looks at another Turing machine being evaluated on itself, and this machine is meant to do the opposite. So K halts if M doesn't halt on M, and K doesn't halt the other way around. K doesn't halt if M does halt on M. All right. And now I ask this thing to evaluate itself. So now this is all possible to make, assuming that we have a Turing machine which can decide whether or not something halts. And now we ask about, now what happens with K hashtag K, all right? So this will say K halts. I'm basically plugging here just K instead of M. But this K works this way for any machine M. So I can use it on itself, and if I write out what those two deals say, I'm just basically plugging in K instead of M. This will say K halts if K doesn't halt. And the second one says K doesn't halt if K halts, right? And this is a contradiction. And all of this means there is no such machine K, which means there is no such machine N, which can tell the difference between a halting program or a halting Turing machine and a non-halting Turing machine. All right, this is a contradiction. All right, the end. This is a very strange kind of proof, and like I said, I'm not aware of other proofs in mathematics that look like this or feel like this. Other than there's other variations of this in the same type of area, but that's that. Okay, so what all this means is, I will just summarize if you've zoned out by now. This means no Turing machine can decide for sure whether or not another Turing machine halts. All right? No Turing machine can decide whether or not. Now, you can simulate, which will tell you if it's it will tell you if it's going to halt, but sometimes it will. If you're simulating a machine which is not halting, then your simulation will also not halt, and then you're never going to know if it's going to halt or not. So no Turing machine can decide whether or not another Turing machine halts. This is a true fact. This actually has sort of real-world practical implications. I don't know if you ever thought about this, but when you, say, are writing a program in Python or whatever, you run your code through the interpreter or a compiler, and a real-life, interpreter / compiler will tell you if you have errors in the code, right? Sometimes this will annoy you because you fix your, you write your code, it doesn't work, you got to fix something or other, and then it still doesn't work, then you got to fix something. This is how it works when you're a programmer. But what I mean by errors here is, like in Python, if you meant to write def but you wrote deft or something like that, it'll say, I don't know what that means, and then you're like, oh yeah, it's not deft, it's def, so you fix it, right? It'll tell you about that kind of error. But the Python interpreter, it won't tell you about if your code creates an infinite loop. Even though that's almost certainly not what you meant to do. If your code creates an infinite loop, the interpreter is just gonna go for it, right? It's not going to stop you. I don't know. Has anybody ever wondered why don't they make the interpreter smart enough to tell if your code is going to have an infinite loop or not? Because that would be useful, wouldn't it? Rather than telling me, this is kind of like stupid errors. I mean, I appreciate them telling me that I messed it up, but it's not all that insightful. Wouldn't it be nice if your compiler could tell you if your code is going to have an infinite loop or not? Why can't it do that? It's because of that. Actually, that is impossible. That is theoretically impossible for one computer to analyze your code and tell if it's going to have an infinite loop or not, right? That's why no interpreter actually does that in real life. So it won't tell you about if your code creates an infinite loop. That's because this would be impossible. The best it could do is try to run a simulation of your code. But then if your code does have an infinite loop, then the simulation will just enter an infinite loop, and that's it. You'll never know anyway. So this would be impossible because, really, it's because no Turing machine can solve the halting problem. No Turing machine can solve the halting problem without allowing for infinite loops. I should really say no. Remember the word, I said this last time, the word total, no total Turing machine. Total means it never has any possibility for infinite loops. No total Turing machine can solve the halting problem. All right? This is important about, the way real-world computers works. And this is when I hope everybody is on the same page here. When I say no Turing machine can solve the halting problem, I don't mean like we just haven't figured out how to do it yet. I mean it's actually straight up impossible for a Turing machine to solve the halting problem, which means it is impossible for your ordinary computer to solve the halting problem, because your ordinary computer is basically a fancy juiced up version of a Turing machine. All right. Can I just say one thing, very little sort of details about this. L is LH, the language of the halting problem. It is RE, but it's not recursive. What that means in ordinary language would be the halting problem. I will say it this way: we can make a Turing machine to verify that a Turing machine halts. That is to say, it is possible, if you already know it's going to halt, it is possible to make the verification on a Turing machine. That is, you just simulate the original thing, and if you already know ahead of time it's going to halt, then your simulation will halt, and that's it. The problem is infinite loops. So it's not recursive. What that means is we can't make, this is a very subtle difference here. We can't make a Turing machine that answers yes or no for whether a Turing machine halts. All right. This is a subtle distinction, and it is a true fact that in real life, sometimes it is, maybe usually, it is easier to verify somebody's answer than it is to create the answer out of nowhere. So what I'm saying is, if somebody already tells you that certain Turing machine is going to halt, you can check their answer easily. But if somebody shows you a Turing machine and doesn't know if it's going to halt or not, that is very hard to tell. All right, that's sort of the difference here. There's a big difference between verifying an answer versus sort of deciding the answer out of nowhere if you don't know the answer ahead of time. Deciding the answer. Right? And this is something probably you have some intuitive idea of. Like, for instance, if I showed you like a Sudoku puzzle, if I showed you my answer and said, hey, could you just check this answer for me? You could check it, fairly easily. You just check all the rows and columns or whatever. Whereas if I gave you the thing with no answer and said, hey, could you just fill in the answer for me? You could do that, but it's much harder, right? There are certain problems where verifying an answer is easy, but deciding the answer out of nowhere is a lot harder. This is actually the basis. I'm mentioning this because this is the basis for a group of problems in computer science which are still unsolved, including the greatest unsolved computer science, mathematical computer science problem. This is an unsolved problem, which maybe you've heard of, called the P versus NP conjecture. Have you heard of this thing? This is commonly called the greatest unsolved problem in theoretical computer science. And it has to do with this question about verifying answers versus deciding answers. And in fact, it's been demonstrated that Sudoku puzzles are of this type. So there are certain types of problems. P means that you can create the answer in polynomial time. That's what the P stands for. That is to say, the problems which are, P is like a categorization of some kinds of problems or puzzles that you can try to compute the answer to using a computer. And P, a problem is in this class P, it means that you can compute the answer in a polynomial time. That's what the P stands for. Whereas NP, the N stands for non-deterministic polynomial, but what that means is you can verify an answer in polynomial time. And Sudoku puzzles are one example of a problem which has been demonstrated to fall into this category. So in a Sudoku puzzle is in the NP category because it's easy to verify an answer of a Sudoku puzzle. But it is not known if it's easy to also create the answer. The best possible for a Sudoku puzzle, the best algorithms to find the answer are exponential rather than polynomial time. All right, and the question is, are these two categories really different? Actually, from a common sense point of view, basically everybody should say they really are very different because there are some problems for which really it is much harder to verify or much harder to create the answer than it is to verify. But actually there are no known examples where those two categories are different. So for instance, Sudoku puzzles are known that you can easily verify them. It is not proven that you cannot easily solve the puzzle out of nowhere. So this is, the big question is P the same as NP? And this is unsolved. This is one of the famous Millennium math problems. There are 7 math problems that have $1 million prizes associated to them. One of them has been solved. The others are not, and this is one of the other ones. Maybe this may be the easiest one to understand, in my opinion. You can explain this to someone without too much trouble. I wouldn't recommend spending your weekends trying to prove the P equals NP conjecture. The answer is probably no. Like most computer scientists would say that the answer is no, but it's not able to be proved. And actually, the conventional wisdom is that we're not even close to being able to prove this one. Some of the other Millennium problems people are feeling pretty good about these days, but my understanding, I'm not in this rat race, but my understanding is that people don't really have much of a clue about how to approach this. Any thoughts? All right. I said something that I said maybe yesterday, maybe the day before, was a Turing machine, if you add new capabilities to it, basically anything that you can think of will not actually make a Turing machine more capable, right? If you let it have several tapes or move the head in weird ways. I said nothing you can think of, and I think I said at the time, actually there are some weird things that you can do which you probably would never think of that would make it more powerful. So now that we know about this halting problem issue, no Turing machine can solve the halting problem, all right? This leads us to an actual improvement on a Turing machine. So we could actually improve a Turing machine by adding an extra feature, I will say a sort of magical, this is sometimes referred to as a halting oracle. If you imagine the Turing machine at any point, ordinarily all it does is read from the tape and then write something and then move to the right or to the left. But if you also gave it the ability at random, whenever it wanted to decide if some Turing machine halts on some input. If it had this sort of magical extra ability, then that would actually make it significantly more powerful because it would be able to solve the halting problem, which an ordinary Turing machine cannot. So we could actually improve a Turing machine by adding a magical halting oracle. This means the Turing machine can sort of follow arrows in the diagram as usual, or it can sort of magically solve a halting problem. If the machine was able to do that, then it really would be more capable than an ordinary Turing machine. All right, this is called a Turing machine with halting oracle. All right. This is an abstract curiosity, although people don't really talk very much about this because such a machine is not possible to create in real life. Like this is why I called this a magical thing. Unless the laws of physics are different from what we imagine them to be, there is no way to create a physical machine that can solve a halting problem. I mean, that there just isn't. So this is called a Turing machine with a halting oracle. This exists as an abstraction you can think about, although it's not a realistic machine that you can build in real life. And what's interesting about this is, turns out there are other languages that such a Turing machine can't compute. So even if you give your Turing machine the ability to magically solve the halting problem, actually there are other problems which still are inaccessible to that kind of machine. It can now do the halting problem, but there's other kinds of problems which cannot be solved even if you know how to solve the halting problem. All right. What about those problems? You could give the machine more oracles that can solve those other kinds of problems. It turns out actually it's been proven that no matter how many oracles you give to your Turing machine, there will always be some kinds of problems which are outside of its reach. So you cannot make some kind of God machine which can compute any language, because no matter how many magical powers you give to it, if you give it like finitely many magical oracles, there are always still going to be questions that are unanswerable to such a machine. Strange but true facts about magical, unrealistic Turing machines. All right, this is all about the halting problem. So the sort of version of this story you can tell to your friends at lunch is what we learned today is that Turing machines, don't say Turing machines, say computers, because that's what computers are basically. There are certain mathematical questions that cannot be answered by computers. If they say, what mathematical questions do you mean? You say, well, the question about will some other computer halt on a certain input? Your friends may not like that. But just the idea, I think, is interesting that there are certain questions which cannot be answered by any real-life computing machine. This, to me, was sort of a surprise when I first learned this. I have a lot of experience doing programming, and I think as a programmer, you always have the basic assumption that what I am trying to get the computer to do, it can actually do. I just have to figure out how to create the program properly. This is not so, though. There are some procedures that actually it's not possible for any computer to do. Not because you don't know how to do it, but just because it's straight up impossible and can never be possible for a computer to do those kinds of things. All right, the halting problem is one such thing, although that's kind of a weird, abstract thing. It turns out, actually, other examples of much more ordinary sounding things have been discovered. So next time we're going to talk about other, I'll just say for now, there's many other, I will say, non-computable problems that, at least on their surface, seem to have nothing to do with simulating another computer or something like that. If they are very ordinary mathematical problems that turn out to have no algorithmic solutions. All right, that maybe we'll stop there. We got 5 more minutes, but let me know if you have questions about